Let's add a few more details to the fundamentals of how the atmospheric response to ocean variability occurs. So this is a schematic illustration of the different physical mechanisms by which the atmosphere responds to variability in the ocean. Warm SSTs near the equator force tropical deep convection, which we looked with the Walker cell, leading to a broad patterns of equatorial easterlies associated with the an atmospheric Kelvin wave. So we have easterlies means winds coming from the east, and Kelvin wave is a gravity wave that typically propagates eastward in the atmosphere, and its speed is like square root gh, like a shallow water wave kind of equation from the ocean side, you may remember. And so you have Kelvin wave here producing easterlies, so basically that's part of the convergence. So if you have deep convection and rising air, then continuity requires that there is convergence, of course, from the Hadley cell side, which we have looked as the zonal mean meridional circulation, but there is also a pull in the zonal direction, as we saw in the Walker cell. Maybe I didn't point out the surface convergence as much as I did the upper level divergence, but obviously you remember there is the convergence as well here, right? A strong convergence in the rising air and divergence at the top. Okay, so that's a big part of this as well. And a stationary Rossby wave here transmitting circulation anomalies into the mid-latitudes. So whenever you have perturbations to the warm SSTs, you can perturb the system and generate waves. It's like somebody pulling the rope that's tied at one end and it sends off waves. So you see that there is stationary Rossby waves. So obviously SST perturbations happen on daily time scales, on weekly, monthly, seasonal, intra-seasonal, interannual time scales, and there are waves, and these stationary waves are always being produced here, which go off into mid-latitudes. Reduced sea ice cover at high altitudes increases surface turbulent fluxes from the ocean to the atmosphere, which warms and moistens the boundary layers and similarly triggers stationary Rossby wave with the potential to impact the storm track and the jet stream. So those typically propagate eastward, but there are details. Warming of the Arctic and the sea ice loss changes pressure patterns over Eurasian region, and these waves can actually come down into the monsoon domain, for example, and create droughts and floods and so on. So lots of details there that you can read up or look at my other podcasts. Potential to impact storm tracks, which are the mid-latitude rainfall patterns that we saw coming off of the North American continent approximately along the North Atlantic current and off of the Asian landmass around Japan in the Kuroshio exit region as well, where we had the secondary rainfall maxima. And we said that's not a dynamical ascent like we had, but it was the indirect cell that we had talked about, where the Ferrel cell and the polar cell meet, causing a rising air. Okay. See, the warm SSTs accelerate the prevailing surface wind by destabilizing the boundary layer, increasing downward mixing of momentum to the surface. Okay, so that is okay, this is always confusing because the lettering is put after the process, so I have to be careful. So this was C here. D is this one. Warm SSTs accelerate the prevailing surface winds by destabilizing the boundary layer and increasing the downward mixing of momentum to the surface. So when you have warm SSTs, sea surface pressure by hydrostatic balance, let's say, decreases, which creates this mechanism of downward entrainment of momentum from the upper atmosphere and affect the surface winds. especially across fronts. This is a very strong process, because if you have a warm and cold SST front that is very sharp, then this process of destabilizing the boundary layer, stabilizing the boundary layer on the cold side, destabilizing on the warm side, can have cross frontal motion, vertical entrainment, and very nice interactions even in the mid latitudes where the temperatures are way below the convective threshold. So these convective threshold responses are more direct, right? So just remember that. Cold SSTs have the opposite effect, to increase stratification, reduce vertical momentum mixing, and ultimately increase the vertical wind shear such that winds are weaker at the surface. Okay, so here where we had cold temperatures, the boundary layer gets stable, so the vertical entrainment is decreased, which means the upper level winds and the lower level winds now have strong gradients, so you get vertical shear, which plays a big role in many situations like cyclogenesis and growth of cyclones and so on and so forth. Horizontal gradients of SST induce gradients of temperature horizontal gradients of SST induce horizontal gradients of temperature throughout a well-mixed boundary layer, which equate to hydrostatic pressure gradient that accelerate wind down the pressure gradient or towards warmer SST, which is here. So we are talking about let's say the cold temperatures in the north of the ITCZ and warm temperatures within the ITCZ, or cold temperatures in the cold tongue and warm temperatures in the warm pool. Especially here where the Coriolis is small, you can have a strong pressure gradient driving strong zonal winds because you have a direct forcing of winds by the pressure gradient. The Coriolis is small, whereas when you go off the equator you have to account for Coriolis as well. So let's look at these two in a bit more detail here. So schematic illustration of the physical arguments accompanying mechanisms D of destabilizing and stabilizing the boundary layer here. So we have warm temperatures, less stable boundary layer. So boundary layer is here, so you can see that the stability is decreased compared to the cold profile or the normal profile, let's say. So warming of the SSTs creates a less stable boundary layer, and there is more downward mixing of momentum from above. So you have a downward pull of the winds here, whereas in the case of colder SSTs or cold to warm SSTs, here you have high sea level pressure, so large integral of rho dz, or mass above this boundary layer, above this surface, so you have high volume of and mass of air. So cold air then is going to reinforce this, whereas you have winds being driven from high sea level pressure to low sea level pressure, especially if Coriolis is weak, and then by the same token you have warm air leading to low air density of air, small weight of the air, hence low sea level pressure. This is basically talking about hydrostatic balance and how cold air has higher sea level pressure because of higher mass above it. Remember, hydrostatic balance just says that the pressure at any level is equal to the weight of the air above. So cold SST has higher weight above, warm SST has lower weight above, so you have low SLP, high SLP, and a wind that goes in that direction. So I'll come back and close this with another example of the air-sea interactions, which is of course the classic El Nino, which you have looked at already, but this gives us another opportunity to look at it in terms of sea surface temperatures, ocean circulation, atmospheric forcing of the ocean and ocean forcing of the atmosphere, and how the system is coupled, so that in the next chapter we can look more carefully at ocean response to wind forcing before we move to coupled climate variability and return to some of the El Nino type feedbacks, and then move on to buoyancy forcing and climate change. Okay?